Here we have a building with a basement. You have the ground floor here and the basement down here. And what we're going to do in this video tutorial is we're going to calculate the U value for the basement wall. The basement wall is looking like this, where we have a plan of the basement here. And we're just looking at this wall here that's going to the outside, not the wall that is going to the unexcavated part, the one that we have over here. So the wall that we're looking at is this wall here. And we have a section where we don't have a light shaft, where we can see how the wall is. And it's made out of these basement blocks here, which we can see if I go to the home page here, where you can see this is the blocks that the wall is made out, where we have the inside of the house here, where we have reinforcement coming up through the blocks, and then we have insulation, and then we have the outer leaf out here. So we have the blocks down here, and then we have a light shaft where we have a window here, and then we have a elevation or detail of the light shaft, where we have the window down here, and we have the bottom of the light shaft down here, and we have the top of the light shaft up here. The way the construction is made is described here. So we have these basement blocks, which I showed before, and from the producers given that these blocks has a U value of 0.16 watt per square meter Kelvin. Then we have some plaster on the inside of the blocks here, and on the outside up here where it's visible, where we do not have the soil. And then we have also here plaster and plaster down here, and then we have on the inside as well, so it's nice to look at. Then we have by the light shaft, we have a lintel here, a slab for the ground floor here, and then we have some insulation with a U value with a lambda value of 0.033, and then we have a lacquer block as the outer leaf here. And then I have written here, if we don't get the right U value, then we could put insulation on the outside here as well, but we don't have that yet. The way we're looking into this is that we have to look at the different U values we have. And first we have U1, which we have here down to 2 meters under terrain. And why it's only down to 2 meters under terrain is that we change temperature on the outside here. If we go to DS 418, that down to 2 meters under terrain, we have -12, and below we have 10. And that we also have over here, right, where we have U1. Then we have U2. And U2 is the part that we have here going out to air under the window in the light shaft. And that's all this part here where we have. So we also take the boundary of the light shaft included here. Then we have U3, which is up here where we have the lintel, which is carrying the slab for the ground floor. And then we have U4, which is below 2 meters under terrain, which we have here. The formula that we're going to use when we have these, I mean, it's the same formula that we use when we look into external walls. The only thing is that's different is that we have lots more different parts of U values that we have to include. We get the formula from DS 418, and we have that here. So here it just said that we have the areas for each U value times the U values, and then we also have, if we have any linear losses, times the length of the linear losses, and then if we have point linear losses. We do not look into point linear losses. And in this case here, we don't have any linear losses. I have rewritten the formula down here, so we have it have all the different U values, U1, U2, U3, U4, and then also the linear loss. But as we do not have the linear loss, then we can delete that. So the bottom part here will be the U value for the basement wall that we have to calculate. So we have to divide it into small parts. So first we calculate all the U values, and after that all the areas to the U value. That's what we need to do. So first we're looking into the U value U1, and that's a part we have down to 2 meters under terrain. So if I jump to the table that we have for the U values here, the form, we can see we are horizontal. So that means that the surface resistant on the inside is 0.13. Then we have this one here, which is the surface resistant on the outside, but that's if it's to air. Now we have to soil, so we have to look at that later. The first thing we meet here is the surface resistance, so that I write in, and that's 0.13. Then the next we meet is the plaster we have here, and we have that from the description of the construction. And we know that has a density of 1700 kilo per cubic meter. So, and we also know that it's 15 millimeters. So when we put the dimension in here, it will be 0.015 meter. Then we have to find the lambda value, and the lambda value we look up in DS 418, right here. DS 418. So I jump to DS 418, and I go to table of contents, Annex F. Here, and then it was 1700. So I'll go up here, and it's curve C, so it's 0.8. That's how I get it. So internal mortar density of 1700. So I go up here and over to 0.8. And I write that. And then I get the R value. And the R value is the resistance, and I get that by taking 0.0015 and divide it by 0.8. Then I know that the basement block has a U value. But for here, I need to put in the resistant, and the U value is equal to 1 divided by the resistant. So the R value must be 1 divided by 0.16. So that means R is 6.25. Then I have to find out what is the resistance for soil. And that I also look up in DS 418. So if I jump back to DS 418 and I jump to the table of content, this here, page 37, and here we can see surface resistant RJ until 2 meters below terrain. H is the depth in meter, and we use this formula here, 0.2 plus 0.3 times the height. So go back to this one here. So 0.2 plus 0.3, and then the depth, the height here. If I go and look at the drawing here, there we can see it's from terrain and down. So the depth is 2 meters. So even though that the first start down here doesn't matter, so it's from terrain and 2 meters down, so it's 2. So put 2 in, so the height is 2. So that gives 0.3 times 2, that's 0.6 plus 0.2, 0.8. And then we add all these together, and it gives us 7.2. And then the U value is 1 divided by 7.2. and then we get this one here. Then we have to think about, do we have any air gaps? And we don't have any air gaps here, so it's 0, so that means this one here is 0, and we don't have any wall ties either, so U1 would be 0.14. So now we have U value 1, which was 0.14. So now we're going to calculate U2. And U2 is the part that we have here, where we are going under the window out to air in the light shaft. So again, we take our form, draw the small sketch so we know where we are. And first we meet RSI, which is the internal surface resistance, and we cross it up here in the form. And we write down here surface resistance on the inside, 0.13. Then the first thing that we meet is plaster again, which has the density of 1700 kilonewton per cubic meter. So same as for U1, but we go to DS418 to the graph here, where we have internal mortar, and we go to the density of 1700. We go up here and go up to the internal curve here, C, and 0.8. And we write that here, and we find the resistance by taking the dimension divided by the lambda value. And again, same thing, now we have the whole block. We know the U value, the reverse, so 1 over 0.16, and we get the R value of 6.25. Then we have the plaster on the outside. So again, we have to go to DS418. We have the density of 1700, and now it's curve D external mortar. So we are on the outside, so we go up to curve D and then over, and we can see here that the lambda value is 0.9. So I go back and I write 0.9 there. And I have the dimension divided by the lambda value, and I get the R value as 0.017. And now it's out to air, so the external resistance I get from up here, 0.04. I add them all together and get 6.48, and then I have 1 over 6.48, and I get the U value, U2, as 0.16, and that's the uncorrected. But as I do not have any air gaps, it's level 0, so no air gaps and no wall ties. So therefore, the U value of 2 will be 0.16. So now we have U2, so we go to find U3, which is where we have the lintel. And that would be a bit different from the others, because if I go to the table for U3 here, again, of course, we have the internal resistance here. I could have plaster out here. Now I just took the lintel, and the lintel is reinforced. That I have to remember when I need to find the lambda value. But the thickness here I have from the beginning in the description of my material. I can see it here if I go to the presentation and I go up here. I can see the lintel is 230 millimeter wide. So therefore 0.23. Then I have to find the lambda value, and that is in DS418. So I jump to that. And here we have concrete. And we have the curves. We have to remember that when it's reinforced, we look down here under conditions. And we have by reinforced concrete with 1 volume percent steel. And that's what we have in the lintel. Then internal is 2.44 and external is 2.54. So we are internal. So if we go here, it's 2.44. And we get the resistance by taking the dimension divided by the lambda value. Then we have the insulation next part over here. We have the thickness of this insulation divided by the lambda value, and the insulation is class 37, so therefore the lambda value is 0.037. And we get the R value by taking the dimension divided by the lambda value. The Leica block here is also given if we go to the description, that we know it's 100 millimeter wide, and we know that the lambda value for this Leica block is 0.22. So therefore we write that into the schedule and we get the resistance. Then we have some plaster on the outside here, and the thickness of that is 15 millimeters, so 0.015 divided by the lambda value, and the lambda value we get from DS418, so we jump to DS418 and we have mortar, and we know that it was 1700 in density, so we go up here, go to the curve D, and then it's 0.9. So that's what we write in here, and we get the resistance by dividing the diameter by the lambda value here. And then we are on the outside, so we have the surface resistance on the outside, which is 0.4. We add all these together and get the total resistance, and then we take the total resistance up in 1, and then we get 0.19. No air gaps. And no air ties, so therefore it is still 0.19. And you can also see here I filled it out, right? But because we times it by 0, it's 0. So now we also have U3. So now we just need to calculate U4, and U4 is nearly the same as U1. Only thing that is different is the surface resistance for the soil. So if we jump to U4 here, we can see we have the surface resistance from the inside. We have the plaster on the inside, same as U1. We have the basement block, and then we have RJ, which is now below 2 meters. And when we are below 2 meters, RJ is 2. If we go to this DS418, we can see here that we have more than 2 meters below terrain, basement walls, then it's 2. So that's where I have it from. Then we add them together, we get the total resistance, and then we have the opposite, which is 1 over 8.399. So the U value will be 0.119. And no air gaps and no wall ties. So the corrected U value will also be 0.119. So here. So now we have all the U values, and I put them into the formula here. So we have U1, 0.14, U2, 0.16, U3, 0.19, and U4, 0.11. So now we have to calculate the 4 areas to the 4 U values. First, we will calculate area A1. And what we have here is that we have U1, that is what we have here around the wall. And we have to take it from the middle here around the wall and then all the way up here. And then, of course, we need to subtract the windows. So if we look down here at where I have written, so here I have the perimeter around. That's this length here around that I have. So I have 2 of these, 4 meters plus the 5 meters. Then I times it by the height, which I have here all the way up to the ring, minus the part down to where my basement wall starts. Then I have to subtract the windows. And I take first the width of the window, which is 1 meter, plus these 2 of the walls of the light shafts. Then I times it by the height of the light shaft, which is these 2 added together plus this length plus this part up here, 0.2. And then I have 3 of the light shafts. 1, 2, 3. So I times it by 3. And this gives this 20.75 square meters. So that's A1. Now I want to calculate A2. And A2 is below ground level with basement blocks next to air. So if I look at it, I have here what is below the basement blocks and is out to air. But this part here also have a window. So what I need to do is I need to take the whole area of this part and subtract the window. So again, what I do is I take the length down here. That's 1 plus the 2 sides that I have out here, times the height, which is the 150, 2 times, plus the 600. And then I have to subtract the window part, which is 1 meter times 0.6. And then again, I have 3 of these windows. So the area of this part here is then 1.71 square meter for the 3 light shaft. So this is A2. Then I need to calculate A3, and that's where I have the lintel above the window. So that's this area here. So again, I take the total length, which is 1 plus 2.15 times 2, and then I times it by the height of the lintel, which is 0.2, and then I have 3 light shafts. So the total area of A3 is 0.79 square meter. So now I just need to calculate the area to U4, and that's when I'm below 2 meters underground. So this is my height I have here, and then I have the perimeter around here. So 4 times 2, right, because I have 2 times, plus 5. And then times the height, which I have over here, 0.57. So the total area is 7.63 square meters. So now I have everything that I need to calculate my U value. So now I put it in to the formula here, and it's really good if you exercise to type it into your calculator. So try and do that and see if you get the same result here. And then we get 0.137, but in the building regulations, all the U values is with 2 decimals. So therefore, we round it up to 0.414. That per meter Kelvin. So this is how you calculate the U value for the basement wall. If we should look at how you should put it up when you make it in the U value report, first you need to get an overview of your basement wall. So you put the drawings into it. So you show how is your basement wall, how is it looking where you do not have the light shaft, how is it looking where you do have the light shaft. And if you have a staircase outside, you also put that in, going down to the basement. Then you write how the construction is, so we know that, and we know all the figures that we need to calculate the U value. Then you write what kind do you have, and if you also have a liner loss, if you have a change of insulation or something, then you also write that in. Then you make a plan and you make your elevations so we can see how it's looking of your walls. And then you can start calculating the U value. And then you divide it up. First, calculate all the U values you have, U1, U2, U3, U4, and then calculate the areas, and then you calculate the U value. So we know that you have everything. So this is the way I like you to put it up. Now look through this assignment here and see if you understand everything. And then you start looking at your own project, how it is. It's really important that you know the layout of your building and the layout of your basement before you can start calculating this. If you calculate it now and you then later change the layout of your basement, then you don't need to change this calculation unless that you have time. So that would be fine. See you in consultation and hope you have fun with this.